Okay, so then right here, find some open space right here and answer this little quiz from your reading. So for number 1, write out the 2 parts of the idea of constant rate of change. And number 2, if the quantity y is a function of x and the quantity is related by constant rate of change, then what does delta y equal? So somewhere below your heading, find a place right there to answer these 2 questions as a little quiz.
Should we add another sheet of paper if we have no room?
Can you just find room? Have it up in the top. Put it up over here.
Okay.
But it's folded so you can't unfold it. So keep it folded. Okay, 1 minute left. If you read it and remember, just write it down when you're done. Seconds. Okay, hand it up. Finish what you're writing. If you're still writing, you can finish up, but hand them up. Okay, let's talk about, first of all, when it comes to homework, make sure that if you don't catch announcements in class or if you miss an email or something like that, so I try to communicate as many ways as I can exactly what's expected, but the final say is always in the assignments area. So if you go to the assignments area, so for instance, due on Wednesday, there were 2 parts. You were to finish that worksheet in class and then complete the questions and the photos. Okay, so go to the announcements page to make sure you're doing all that's required. Let me talk about this coming Wednesday's homework. There are 3 parts to it, so I won't see you for almost a week. And then our exam is next Thursday, so the homework for Wednesday is longer and important. And so let's just talk very quickly through it here. Let me just move it up first. Okay, so the first thing is number one is to complete this worksheet. That's a short worksheet. Follow the instructions very carefully. If you have a laptop, you're not going to email me anything. I'll be doing a check in class. If you have a graphing calculator on a computer at home somewhere else, then you're going to be emailing me. Follow the instructions very carefully. That's half of the battle, and this part of the assignment is following the instructions, but the rest of it's pretty small. Okay? Second part. At the end of class today, I'm going to give you a packet of work. You have all of recitation to work on it. And you're going to want to go and show up and work hard on it while Owen is available. Get as much done of it as you can. Okay? I'm going to hand this out at the end of class. This is probably the longest part of your homework due. Okay? And this is really important. And then number 3 is some more reflection questions like you had for today. So from this same chapter 1, part 1, more reflection questions. So 3 parts to Wednesday's homework, all important for next Thursday's exam. Okay? Then I have office hours on Tuesday, and so whatever start early, and then come to my office, and we can talk about what you're having difficulty with, and then you can have it complete for Wednesday. Okay, about the exam on Thursday, if you go to quizzes and exams here, I've opened up the area called Exam 1 and Associated Quizzes. And I have a bullet point of what's covered on the exam. And then I have the blank copy of Quiz 1 that you took last Friday and the solution key. You won't have a quiz and recitation. You'll just be working on that packet. So there's only one quiz that pertains to the content on this particular exam. And so there's your bullet list. Okay, also sometime in the middle of next week, I'll start posting some solutions to some of the homeworks. And those will be posted right where in the homework section, right by the assignment. There'll be solutions posted. Okay? So thinking about all this homework that you're doing for Wednesday, think of it not only as getting this assignment done, but you're getting ready for the exam too. All right, any questions about homework or exam 1 next Thursday? Okay. You guys good?
I was just asking, do we take all of them in the testing center downstairs?
Yep, all the exams will be just like you did the pretest. It'll be Thursday on your own time. Go between 10:30 and 6:30. Bring a sun card. You can have you are allowed to have a calculator for the normal exams. And we'll talk about that next week. Okay, so today we're going to spend the first half of class talking about constant rate of change as a follow-up to your reflections that you did for the homework. And then the second half we'll do more graphing calculator stuff, okay? Okay, so let's start with a review of the meaning of quotient, okay? Because rate of change is all about, we talked about at the beginning, rate of change is really about quotient, division and quotient. So just take a second here. Suppose quantity A has a value of 17, quantity B has a value of 5. If you divided 17 by 5, you get the number 3.4. So in terms of quantities A and B, what does the number 3.4 mean? Talk to your partner. Go. So in terms of the quantities A and B, what does that number 3.4 represent or signify? Talk to your partner. Is Connor here? Connor Simpson? How about Andrew? Is there a different Andrew, or Andrea? Andrea. You know Andrew? Is that you? You're supposed to have a lively conversation. Everyone should be in a lively conversation. Are you done already? Connor Simpson. It's you. Okay, so there's more than one way to say it. Here are some possibilities. 3.4 is the size of A relative to B. Did anyone get that? 3.4 is the size of A relative to B. 3.4 is the measurement of A in the units of B. So if we were to take B and use it to measure A, it'd be 3.4 of B to get A. It's another way to say it. A is 3.4 times the size of B. These are all ways, and there could be more ways to phrase it. That's what the meaning of that quotient is. Any of those. Okay, with that in mind, so let's make it a little more practical here. Can I go on? Here we go. So suppose every 40 milliliters of water poured into a container causes the height to increase 7.5 centimeters. So consider 7.5 divided by 40, which is 0.1875. What's the meaning of that number? What's the meaning of 0.1875 in terms of the volume and height? Go. So you start by saying 0.1875 is, what does it mean? What does that number mean?
So is that milliliters per centimeter? Because it's like, okay, so here it says you have 7 or not 7 meters per milliliter. So it's what 1.874 as milliliters is the number of centimeters that each single milliliter of water like causes the height. This, if you look at it like this one.
So I would guess that many of you are talking about the quantities of volume and height. But really, what is this talking about? Is this really talking about height and volume? What's this talking about? What's that? We're not there yet, so I'm just talking about the quantities themselves. Are the quantities themselves volume and height of the water? Is that what this is talking about? What is it? If not, what is it talking about? This goes back to your homework.
How many centimeters per milliliter of water you're like scaling it down.
Okay, but just the quantities themselves, yeah. What's that? So we're not even there yet. So I'm not to relative size or rate of change. I'm just asking what two quantities are in question here. Okay. So this is from your homework. This is talking about changes. This is talking about changes. It's not talking about the height versus the volume. It's talking about for every 40 millimeters I pour in, the height will increase so much. That's talking about changes in volume and changes in height. Does that make sense? Like, do you see that the volume and height are not in this container right here? They couldn't be related by this 0.1875. Do you see? But starting here, if I start adding 40 milliliters or 20 milliliters, starting at this point in the container, the change in volume and the change in height are related by 0.1875. Do you see? That was what your reflections were talking about. Okay, so the change in height is always 0.1875 times the added volume. So it's not that the height is 0.1875 times the volume. It's a change in height. Say starting from here. A change in height is 0.1875 times the change in volume. Another way to think of it, the change in height is always 0.1875 relative to the number of milliliters added. So what we're saying is this is a constant, that quantity is a constant, that ratio. Okay, is it familiar at least after previous discussions and your homework? Anybody have a question? Okay. So what are the two parts? Here's your quiz. What was the first part of the idea of constant rate of change? Yeah, Lauren. Okay, two quantities change simultaneously, and what was the other one?
The other one was that
This one quantity changes in ratio to the A to B.
Lots of different guesses here. One quantity is proportional to the other. Is that right? The one quantity is proportional to the other. Is that right?
yes.
Everyone agree? Someone's shaking their head. Changes in the quantities are proportional. The quantities themselves are not necessarily proportional for constant rate of changes. Changes in one quantity are proportional to changes in the other. That's different. That's different than just the quantities being proportional. Okay, so and this was the second part of your quiz. What do changes in y equal? We're going to see this over and over and over all semester long. Do your best to learn it right now today, and then be on the lookout for it. When does it apply? Because it's going to show. We're going to keep returning to this. It's a key idea in all of calculus that changes in y are proportional to changes in x, meaning that every change in y is a multiple of its corresponding change in x, and that multiple stays the same. So this is like you want to calculate a change in your output value. If you have constant rate of change, it's k times whatever your change in x was. Okay, then the second part of this is that every change in y has the same size relative to its corresponding change in x. So I said that. Forget that I got this thing. What did we say? We said for every change in how much volume did I put in that previous example? Caused what? How much? Okay, so what is the change in height relative to the change in volume? What was it? 0.1875. So what if I put in 80 milliliters of volume? So we know this came from 7.5 over 40. So what if I put in 80 milliliters? Yeah, it would go up 15 centimeters, right? The height of the water would go up 15 centimeters. So this is this idea of relative size. The amount that the height goes up is always 0.1875 relative to how much water you put in, right? Now, suppose I want to know if I change the height, if I change the volume, so that's this part. So this right here is this. Okay, suppose that I change the volume 400, I don't know, let's say. Suppose I change the volume 92.3. How would I calculate the change in height? So I'm changing the volume, I'm adding 92.3 milliliters to the bottle. How would you calculate, not what's the answer, but how would you calculate the change in height? If changes in height are always 0.1875 relative to changes in volume, then how would you calculate the change in height?
Just multiply it to 0.
Yeah, so changes in height are always 0.1875 relative to change in volume. It's that much of a change in volume. So you multiply. Okay, so this then is an application of this one. Given a change in volume, if this is changes in height relative to change in volume, then we want that much of that change in volume to get the new change in height. Okay, so absolutely crucial. So study this over and over again. Memorize it, okay? So there's some situations where memorization is very important. This is something you got to memorize, and then we got to be on the lookout constantly to apply it throughout the course. And we'll go over it again. Anybody have a question? Okay, so here's using the bars. Now, we've not used the bars to represent a change in the quantity. So here's the top bar representing a change in y, and the bottom bar representing a change in x. So where in this picture is just the quantity y? So if this is a change in y, how could we imagine in this picture what just the quantity y represents? What's that? What do you mean?
I said at the beginning, because if you start there, all that is the change of it.
Okay. Yeah, so maybe it would be like there's something over here. And that would be like y. So we had the quantity y, and then we changed it this much. We increased it that much. Do you see? And maybe x to start with. Maybe x was this much. And then we increased it. So we had a corresponding value of y and x there at the left end. And then we increased x that much, and y increased, correspondingly, y increased this much. Okay, so this next illustration then shows obviously a smaller change in y and a smaller change in x, right? But is there anything the same about these two? So the changes are different. The change in y is smaller, and the change in x is smaller. Okay, so the proportion between the two remain the same, and they're constant. Anybody else? What stays the same? The rate at which they change. Relative size. Is the relative size the same? What would you predict the relative size of y changes in y with respect to changes in x? What would you say the relative size is? Which we're calling k, right? So we're calling k the relative size. What's that? He said 2 and a little bit. It's a little bit more than 2. So what do you want to say? 2.1? We're guesstimating. So if we took delta y and divided by delta x, we would get? What about, so it's the delta y 2 over delta x 2? .1 again, right? So the changes are different, but the relative size is staying the same. What about this one?
Same.
Again, changes are all smaller, both smaller, but what's staying the same from each example to the next is the relative size of changes in y to changes in x. So this is the idea of a constant rate of change. In this case, 2.1. Changes in y are 2.1 times changes in x, or 2.1 relative to changes in x. Okay, huge idea. And this is what we said. Every change in y is a multiple of its corresponding change in x. What multiple did we say that was? 2.1. So, delta y1 equals 2.1 delta x1. Different change in y, but it's still 2.1 times its corresponding change in x. Still a different change in y, but it's still 2.1 times its change in x. Constant rate of change, right? The constant is 2.1. Every change in y has the same size relative to its corresponding change in x. 2.1. It's always 2.1 relative to the size of the change in x. Okay, and so this is about all these reflections that you're doing in the homework. And we got some practice here. So after a car goes under a bridge, it travels at a constant rate, a speed of 72 miles per hour, meaning the number of miles it travels for some period of time is always 72 times the number of hours in that period of time. So taking the situation, can you identify what would delta y be? See if you can figure this out. So in this situation, what phrase or number or word is talking about delta y? Go. Okay, Richard, you're up. What do you think? What part of this description would be delta y? What should I underline or circle here for delta y? So what phrase or word from here? Number of miles it travels. Okay, so if you want to include for some period of time. Agree? Is that delta y? Okay, what about delta x? Some people are saying number of hours. Agree with that? And what is K?
72 miles.
You're so smart.
Delta y equals 72 times the change.
Okay. What's that?
Delta y equals 72 times delta x.
Marcus is adding this statement. Agree with that? Changes in y are always 72 times changes in x if we're going 72 miles an hour. So changes in distance are always 72 times changes in time. Agree? What would y be in this? How can we define the quantity y? If delta y is the number of miles traveled, it's kind of like an additional number of miles, right? So what is the quantity y exactly?
The number of miles the car traveled before it went under the bridge, before it goes under the bridge.
Good number of miles to travel before it goes under the bridge. It's not an initial. It's a changing quantity too. Okay, so what is that quantity y? Yeah.
Number of miles traveled.
Total number of miles traveled. So we need like a reference point. We need like a starting point. So like since the bridge, right? So this would be like total number of miles traveled since the bridge. And what would x be? Number of hours since leaving the bridge. So do you see the difference between xy, delta y, and delta x? Okay. To have constant rate of change, it's talking about the quantities of additional or change in these original quantities. That's the focus of constant rate of change, is the changes in the quantities, not the quantities themselves. Okay? So if after driving a little while, the car travels another 1.6 hours at a constant speed of 72, and during that period of time, the number of miles the car has traveled increases by 72 times 1.6. Go.
You would actually have to multiply out.
Or it's just that,
Or x would be forward.
that like that equation.
Well, yeah, we don't know x.
But it, yeah, but it was changes
Changes to
Change in x.
1.6.
1.6 hours. Constant rate of change.
72.
Delta y. K times delta x, or 72 times 1.6. Okay, so so go back to those reflections that you did for today, and then you also have the reflections for Wednesday. This is what you're practicing. Looking at a situation and really identifying what's y, what's x, what's the change in y, what's the change in x in a given situation. And then making sense of constant rate of change, which says that changes in y are always k times changes in x. And the size of the change in y is always the same relative to the size of the change in x. And that's our constant rate of change. That's that k value. So you got to practice this. You got to practice this, okay? Any questions about that? Okay, so let's go back to graphing calculator. Don't quite open up yours yet, okay? So just hold off for a second. So I just wanted this, remember this thing?
Scale.
Talking about how the quantities are changing together. Okay, so this whole demonstration that I did when we were teaching about these bars and how the covariation of the two bars, this is all made on graphing calculator. This is a graphing calculator. Okay, so remember we flipped up the dependent variable bar. We said let's put a plane on the top, and we said let's track where it goes. And then we said what is that? What does that curve represent? The curve represents all the points of corresponding values of the red bar and the blue bar. Okay, and then we said this is really what an XY graph is, right? Where the red bar would be, can't really see that, but the red bar would be our X quantity, and the blue bar would be f of X. And we're tracking off the points of those two, of the input and the output, and how they change together, and all the corresponding values of X's and inputs and outputs. Okay, so the instructions are not like, it's not visual instructions. The instructions are purely mathematical. So to write these command lines, the command lines are purely the mathematics that generate the things that you're seeing. Okay? So that's what this thing is. It's a mathematical calculator that takes what you tell it mathematically and then shows you the visual representation of it. Okay? So that's what we're learning. Okay, so let's talk about, we've talked about using it as a calculator, so now we've got to talk about how does it actually graph things. So we said that when you put in letters, like if I said D, so what does that equals 1 mean? It means it's a free constant, free parameter that I can assign to different values. Okay? But there's certain things that are reserved for that can't be used this way, and two of those are X and Y. Using X and Y in command lines are indicating to graphing calculator, X is indicating all the X values on the X-axis, and Y is all the Y values on the Y-axis. Okay, so to graph, so the one easy way to graph is just to type in y equals x squared, and as soon as you hit enter, it will graph it for you. So no function notation used. Okay, no function notation used. Okay, so if for just this part, if you would please not do what I'm doing, just watch, and because I'm going to have some questions and I don't want you to jump ahead of me. I want you to think about some stuff. Okay, so now I can define a function, say call it g, and how do I make it a function? Control 9, not shift 9. Control 9, now that establishes that it's a function, and I'm going to say gu equals, say, u cubed. Will it graph the function g? Yes or no?
Yes.
No, because I haven't used x or y. Okay, remember, x and y are what indicate or signal to graphing calculator that we want to graph. So all I've done is notice that there's no square there anymore. I've just established that the g function is to take the input and do what to it? Cube it. All right, whatever the input is, it's going to cube it. Okay, so now, so if I wanted to graph it, I need to write y equals the function. So what if I do this? Y equals the function. Don't do this. I want you to think about it. Control U. What is that going to graph? What will that graph?
X squared equals u cubed.
No, y is not a parameter. Y is the y-axis. We can graph many graphs at once. Y will always mean the y, all the points on the y-axis, all the values on the y-axis. So there's no relation back to y equals x squared here. That's just telling it to graph x squared. And this is also telling it to graph g of u. What are we going to see? We're going to see the graph of something cubed? Is that what we're going to see? What happened? Oh, I shouldn't have used u. So I'm going to go back here, sorry. U is also reserved for something else. So I'm going to do K, okay? Or D. We said D, so let's do D. Sorry about that. Okay, is it the same as before? All right, now, so now same thing. G of D. What will it graph? All right, so I'll turn this one off, just focusing on that G function. So I turned off x cubed. So what will you see when I graph this? No. What happened?
D equals 1.
What's that?
D equals 1.
D equals 1. Julie?
Since you've already defined the function g, all you have to do is plug in g of x.
No, I'm asking what happened. Yeah. No, I got a graph. It's graphing y equals g of d. It's graphing it as this horizontal line at 1. Yeah, is it David? Yeah.
I graph y equals 1 for every point
Why did it do that?
x. Because g of d cubed,
Okay.
that, so g of d is d cubed,
Right?
and d is defined as 1,
Yep.
so it's just 1.
I never said what, so here, d is what's called a local variable. Meaning, in just this line, it stands for the input of the function g. But what is the value, and any other line, what is the value of d? 1. So by saying g of d, what is it telling graphing calculator to do? Oh, just g of d. What is that? It's 1 plugged into this function, right? It's the output of g when d is 1. So that right there is the number 1. And so we're graphing y equals 1. Does that make sense? So what if I set d equal to if I set d equal to, say, 0.7. Now what's the graph going to be? Now it's graphing 0.7 cubes. Do you see that? So what do we want to do? We want to graph the actual function of g. What should I do? What command line should I write to graph the function of g?
Y equals d of g equals d cubed.
So it's back here. Y equals what? If I want to graph the function g. Yeah. Is that you involuntary response? Or you raise your hand? No? No. Yeah.
Y equals
G of x. What does x stand for? X stands for every x value on the x-axis. So it's going to take every x value. It's going to find the corresponding output, and it's going to graph it. For each value of x, it's going to give you a y. And now you've got all the points on x cubed. Do you see? Does it make sense? Yeah.
Could you possibly in the second line there put d equal to x and get the same result?
So here's the thing. There's nothing special about d. When you're using the function g, it doesn't care about d. It's just this is the local variable we used for the input. So when you invoke the function g, all it's going to do is take what's in the parentheses, no matter what it is, and it's going to cube it. It's not really thinking about D. So the function G doesn't require D. It just, you have its set of instructions. Input and output will be whatever the input is cubed. So there's not, when you're using G, you don't have to use D. D is just the local variable in that line. That's the input, and then the this tells what to do with that input. Okay, so suppose I want to restrict this. I just want to show it from 1 to 3. So what you can do is take that graph, do comma. Now you can play if you want. Okay, you can go ahead and work. Okay, so I can do 1 is less than x is less than 3. What is that doing? That's going to just graph G from 1 to 3. Am I seeing all of what I specified? Am I seeing all of it? Am I seeing all the x values from 1 to 3 here? No. Okay. So you have the ability to zoom in and zoom out down in the lower left-hand corner. Okay. So the one on the left means zoom out, and the one on the right means zoom in. So I'll zoom in first. When you zoom in, it zooms both axes. Is this a better view or a worse view? Worse. Okay, so I want to zoom out. Am I seeing everything now? Getting closer. Am I seeing everything now? So really, if I want to see this piece of this graph from 1 to 3, what I'd really like to do is just kind of look at this much in x, and I need to see even more of y, right? So if you hold down Control or Option, you notice that you get these left and right arrows. So that means I can just zoom in or out on the x-axis. So what do I want to do? Zoom in on the x-axis or zoom out? I just want to see, say, from 0 to 5. I'm going to zoom in on the x-axis. And then if I hit Command, I get the up and down arrows. Do I want to zoom in or out on the y-axis? Out. So that's a pretty good view of what I wanted to see. So notice the scales are different now because I zoomed in on the x-axis and out on the y. So now my scale is 1, 2, 3, 4, 5, 6, and then on y it's by tens. But this is a nice view of this part of the G function. Okay, does it make sense?
How do you get the grade then?
Shift comma or Shift plus. Should be on your keyboard, right?
Yeah,
Is it?
Just won't graph it. So it can't graph the equation in this form.
You're doing something's different than what I put up there. I can look at it later. Okay, so let's quickly look at. So this was the function we ended with on page 3 last time. Remember that? So what I want to do now is I want to graph this function with the input being number of pay. This was the amount of your monthly payment. The output of this function, it was spitting out how much your monthly payment would be for a given interest rate, initial loan amount, and number of payments that you wanted to make in the loan. So I want to graph for varying number of payments what the amount of the payment would be. So I want y to be my f. Okay, and let's make the rate, say, there on page 3. We'll use 260,000. And let's make the initial, that's not the rate. What's the rate? 0.0625. This is on page 3 from last time if you have it. And the loan amount, 260,000. And so if we want to graph it for different amounts of payments, what am I going to put here now? N? What am I going to put? Hello. Anyone home? X, right? So if I put n, it's just going to, all it's going to do is graph it for whatever the current value of n is, and if I don't specify, it will be 1. So, but if I want to see it for different values of n on the graph, then I need to put x there. So let's graph it. Okay, there it is. Why don't we see anything? It's all, we're graphing these, it's all about knowing what these quantities are, okay? What quantity is on the x-axis? Yeah, but what quantity does x represent? What are these values on the x-axis? Number of payments in the loan. So what's typical? Does anyone know for a house loan, what's typical for a number of payments in the loan? 180, 360, right, so like a 15-year loan would be 180. A 30-year loan would be like 360. Okay, so this is a nice scale to look at number of payments. I still don't see anything. Why not? What's the output? What's the output of this function? What quantity does it represent? The amount of your payment. Is the amount of your payment going to be $1, $2, $3, or $4, $5? What do we need to do? Zoom out. So what's a typical payment, say, on a $260,000 house? How much would you pay per month? Yeah, in the thousands, right? Now notice, do we want this part of the graph? No, because this would be like a negative number of payments. Doesn't make sense. So let's just go from, we're going to just specify this from 0 to, say, a 30-year loan, 360. Okay, so we talked about scaling. If you click on the graph, you get crosshairs, and then up here in the upper left, I know I'm keeping you late, but I'll give you the time back another day. You get the ordered pair up here of what it is. So this particular ordered pair right now that I have, and then you can drag it. So you can get on the crosshairs and you can drag. Okay, so let's do this. So right there, x is 60, and y is 5056.81. What does that mean? So what is the meaning of that in this context? X equals 60, y equals 5056.81.
With a 6.25% interest rate on a $260,000 loan,
Right.
over 60 months, you're going to pay $5,056.81 per month.
If you chose your loan to be a 60-month loan, right? So this is different. Every X value is a different loan in terms of how many payments you're choosing to make. If you chose your loan to be a 60-payment loan, then your monthly payment with those other parameters would be like around $5,000 a month. So if you choose to make more payments, does it make sense that your payment would be lower? Yeah, the more payments that you make over a longer period of time, you're going to pay less for each payment. And so that's why this is a decreasing graph. Okay, so we talked about the crosshairs. You can get points just by dragging. Okay, you know how to scale the axes. You know how to take part of a function that you're graphing. I think that's everything you need for that. You have a short homework assignment that deals with this stuff, and then you have the packet that you're going to work on in recitation. Anybody have a question? So the packet is a combination of, you're going to continue to learn more about graphing calculator, but then it's also testing your knowledge about function notation. So graphing calculator, it takes function notation and it shows it to you visually. That's what it does. And so you really have to understand that. Okay, so you can take one of these on your way out, bring it to recitation. I'll just give it to you. Have a a good long weekend. Email me if you got a question, or I'll see you in office hours on Tuesday.
Mark, you wanna help me with this?
Yeah. You never define what G was.
Oh, okay.
You gotta define what G is, right?
Oh, okay.
It doesn't, you never told it what the function G is. So you can't correct it.
And then this one right here.
Okay, so, so what you're saying is payments from 200 to 600. Number of payments is.
How do you change that?
Roll if you Yeah.
I just wanted to excuse myself for being late.
Oh, I didn't even notice.
Well, yeah.
Was it just today?
Yeah.
Oh, okay, I didn't even notice.
Usually it's happened. I don't know if I missed anything.
It'll be in the video.
Okay.